सर मोलर प्रॉपर्टीज समझा है लेकिन कल का थोड़ा सा क्लियर नहीं हुआ था.
Okay, so yeah, okay, so let us understand molar property is property of pure solvent. I'm talking about solutions. So there's a solute and a solvent, right? If you take ethanol water and we dissolve ethanol in water, so water is the solvent and ethanol is a solute, right? If you dissolve water in ethanol, I mean more fraction of ethanol, then water is a solute and ethanol is a solvent. Depends concentration of it. It doesn't matter. One is solid, one is solvent. So when we say molar volume of water is 18 ml, it means 1 mole of water, pure water, occupies 18 milliliters. Right? Is that clear?
Yes.
Okay, so now if we take pure water and mix it or add to say ethanol, or take ethanol, ethanol का molar volume कितना है pure ethanol का? You seen last week, right? 57 something like that, right? 50 around 50 plus ml. So 1 mole of ethanol has molar volume around 57, 56, 57. Now if you take pure water, say 1 liter, and add say 1 mole of ethanol to it, how much is the contribution of ethanol to that solution volume when we add it to a large volume of water is the partial molar volume. Partial molar volume is contribution of ethanol when we add a small quantity of ethanol to a large volume of water. That's what it means, partial molar property. Partial molar property is always for a solution, whereas molar property is for pure liquids. Understand the difference between molar property and partial molar property. समझ में आया प्रतीक्षा मोरे?
हाँ सर.
So if you understand that, that means partial molar volume is if you add ethanol to water, any concentration of ethanol water solution, it can be pure water, it may be 30% ethanol in water. If you add some ethanol to a solution of ethanol in water, then what is the contribution of that 1 mole of ethanol to the solution of ethanol in water? That is partial molar volume of ethanol in that solution. And we solved a problem also last week on all these concepts. Molar volume, partial molar volume, we solved a problem. Okay. So now moving forward, chemical potential is partial molar Gibbs free energy. Just like partial molar volume, chemical potential is nothing but partial molar Gibbs free energy. What does it mean? It means if I have a solution of ethanol in water and I add 1 mole of ethanol to that solution, what is the contribution of that 1 mole of ethanol to the Gibbs free energy of the solution? Just like partial molar volume is contribution to volume of the solution, partial molar Gibbs free energy is contribution to the Gibbs free energy of the solution. समझ में आया? प्रतीक्षा मोरे?
हाँ सर. हाँ सर.
बाकी लोग को समझ में आया?
Yes, समझा सर.
समझा ना? And Gibbs free energy, why we are considering Gibbs free energy? Why do we consider Gibbs free energy? Why not Helmholtz energy? Why we are looking at contribution to Gibbs free energy, not to Helmholtz energy?
Sir, because of constant temperature and pressure, we consider it.
Because most of the systems in chemical engineering are at constant temperature and pressure, and those conditions, what we get is net work done by a system is given by Gibbs free energy, whereas Helmholtz energy is at constant temperature. So if you have a system at constant temperature, we have to use Helmholtz energy, but we have systems mostly at constant pressure and constant temperature. That's why we are considering gives free energy, and we are seeing what is the contribution of a component when it is added to a solution, and to that gives free energy of the solution. ठीक है? Any doubts? समझ में आ रहा है significance of partial molar gives free energy, which is nothing but chemical potential. उसका नाम दिया है chemical potential because that decides, that represents the what you call gradient or driving force for chemical equilibria or phase equilibria. And chemical potential is similar to temperature for heat transfer, which is the driving force for heat transfer, and pressure for fluid flow or mechanical equilibrium. So understand the difference or comparison with driving forces for different equilibria. Temperature is for thermal equilibria, pressure is for mechanical equilibria, and chemical potential is for chemical equilibria or phase equilibria also. So is it clear now?
Yes, sir.
और किसी को डाउट है कुछ बिफोर यू प्रोसीड फर्दर? डाउट है तो पूछो अभी. Okay, so we had done some derivations. We did for partial molar volume, and now we did yesterday for partial molar gives free energy or chemical potential. Same thing. वो हमने निकाला था molar volume of solution was partial molar volume of component 1 into x1 plus partial molar volume of component 2 into x2. ऐसा था, right? Can you see this PDF?
Yes, sir.
So
Yes,
instead of volume, now we have gives free energy. So gives free energy of a system solution G, capital G, is equal to mu1, which is partial molar gives free energy, into x1 plus mu2, which is partial molar gives free energy of component 2 into x2. Exactly similar to volume equation. ठीक है? Derivation exactly similar है, इसमें ज़्यादा कुछ नहीं है. So let us move. So chemical potential is the important property of solution used in study of phase equilibrium and chemical equilibrium. Reaction रहेगा तो उसमें भी यूज होता है. We'll see that in unit 5 and 6, and phase equilibrium is unit 1, 2, 3, 4. So that's why we have to work with G, which is representing the driving force for chemical equilibrium and phase equilibrium. Okay, so once we have this concept of chemical potential, then we need to see what is the effect of temperature and pressure on chemical potential, because although the system operates at constant temperature and pressure, if you change the pressure, what happens? If you change the temperature, what happens? So we need to understand that also. Okay, so by definition, mu I is nothing but partial molar Gibbs energy Gi bar, and by definition that is equal to dava Gt, total Gibbs energy derivative with respect to dava Ni, component I, at constant temperature, constant pressure, and constant n subscript j, where j is not equal to I. So by keeping all the other components constant and changing only I, we add a small quantity of I to the solution. How does the total Gibbs energy change? That is our mu I. Understand this definition of chemical potential, right? Any doubts on this? Because this is our basis for everything else. If you don't understand this, we are not going to understand anything else. ये क्वेश्चन समझ में आया सब लोगों को? By definition, this is what it is. Partial molar property. Okay, so differentiate this with respect to pressure. What we'll get is dava mu I by dava P at constant temperature and N, because we are changing pressure, taking derivative with respect to pressure. That is equal to dava square Gt by dava P, dava Ni. Okay. Now we know that dg is equal to vdp minus sgt, or for total properties you can write dgt is equal to vt into dp minus st into dt. So differentiate with respect to pressure at constant temperature, and second is with respect to temperature at constant pressure. So if we take derivative with respect to pressure at constant temperature and n, right? So constant temperature में dt 0 हो जाएगा ये. So what will get is vt, ये इधर से इधर आ गया. And if we take derivative with respect to constant pressure, dp will be 0, and derivative with respect to temperature. So dou gt by dou t at constant pressure, and n is minus st. Is this okay? Is this clear? How do we got this derivative? Question है, doubt है तो पूछो immediately. Don't hesitate. You can ask n number of times. That's not a problem. Okay, so let's go. Now once we have this derivative, take a second derivative with respect to ni. So do we get dou square gt by dou p dou ni is equal to dou vt by dou ni at constant pressure, temperature and nj, that j is not equal to I. Right? So if you compare this equation 1 and equation 2, the right hand side here and left hand side here is same. Right? So what we'll get is dou mu I by dou p at constant temperature and n is equal to dou vt by dou ni at constant pressure, temperature, nj, where j is not equal to I. And by definition, what is this thing? It is nothing but partial molar volume, Vi bar. So that is the effect of pressure on chemical potential. So if we change pressure, it will change, it will be directly proportional to the partial molar volume. Any doubts, questions on question 3? Is it clear to everybody? Question 3 कैसे आया? Okay, so if you are clear, let's proceed further. So this is the effect of pressure on chemical potential. Now we'll see what is the effect of temperature on chemical potential. So by definition, this is what is partial molar Gibbs free energy. Now we take this, take the derivative with respect to temperature. So what we get is dou mu I by dou t at constant pressure and n is equal to dou square gt by dou t dou ni. Again we start with this dgt is equal to vt into dp minus st into dt. Take the derivative with respect to temperature at constant pressure. What we get is dou gt by dou t at constant pressure is equal to minus st, which we did before also. And we are going to take this equation and take a derivative with respect to ni. So for pressure we had taken this thing as starting point. For temperature we take this as starting point because we want variation with temperature. So second derivative will be dou square gt by dou t dou ni is equal to minus dou st by dou ni at constant pressure, temperature and subscript j, where j is not equal to I. Right? So if you compare equation 1 and equation 2, this left hand side and this right hand side is same. So what we'll get is dou mu I by dou t at constant pressure n is equal to minus dou st by dou ni at constant pressure, temperature, nj, j is not equal to I. And what is this thing? By definition, this is partial molar entropy. Si bar minus is there. So this is partial molar entropy of component I. Any questions on equation 3?
So could you please repeat?
Repeat, okay. So,
So from DGT onwards.
from
The
DGT
equation
onwards.
DGT is equal to
DGT is equal to
yeah.
VT dt minus ST dt. Now we take derivative with respect to temperature at constant pressure. So what you get is dGT by dou gt by dou t at constant pressure is equal to minus st. Right? This is not required. This was already used in the effect of pressure. For temperature effect, we have to use this second equation. Now take derivative with respect to Ni. What we get is dou square gt by dou t dou Ni is equal to minus dou st by dou Ni at constant pressure, temperature, Nj not equal to I.
Okay, sir.
Okay. So we compare equation 1 and equation 2. This left hand side and this right hand side are same. Dou square gt by dou t dou Ni. So this left hand side and this right hand side has to be equal. And that's what we have written. Dou mu I by dou t at constant pressure N is equal to minus dou st by dou Ni at constant pressure, temperature, Nj not equal to I. And this is nothing but partial molar entropy of component I by definition. Okay. Anybody else has any question on question 3? Okay. So if there is no question, we'll proceed further. But what we need to do is, we cannot measure entropy. Entropy is something we don't measure. It's not directly measurable. So we have to find equation in terms of measurable properties. For pressure, we saw that it is VI bar, and VI bar we have seen we can measure, we can calculate. We have also calculated, right? From the graphical figure, we saw how to calculate or evaluate VI bar. So this is okay. We can actually evaluate VI bar and calculate what is the effect of pressure on mu I. But for effect of temperature, it is equal to minus SI bar, which is partial molar entropy, which is not a measurable quantity. We cannot measure it. We cannot evaluate it directly. So we have to get a correlation of SI bar in terms of something measurable. Okay. So we use this equation. G is equal to H minus Ts. So if you can write the same thing in terms of partial molar properties. So Gi bar is equal to Hi bar minus Tsi bar, or this is nothing but mu I equal to Hi bar minus Tsi bar. So we can take Hi here and divide by T. We get minus Si bar is equal to mu I minus Hi bar divided by T. And we know that this is nothing but minus Si bar. That's why we are doing this. Okay. And then we need to have so we need to evaluate, we represent in terms of this one. So we are taking derivative of u by v, if numerator and denominator is there, that is equal to denominator into derivative of numerator minus numerator and derivative of denominator by denominator square. If we take mu I by t, here it is mu I, but normally mu I by t is there, term is occurring normally. So we have taken derivative of mu I by t with respect to temperature at constant pressure and N. Is nothing but denominator is T into derivative of numerator is dou mu I by dou T. Sorry, denominator is T here. T into derivative of numerator is mu I, dou mu I by dou T, minus numerator is mu I into derivative denominator is dt is 1 and divided by T square. So equation 5 is okay. Are you clear about equation 5, how we got it?
Yes, sir.
Okay. So now we substitute equation 3 in 5. What is equation 3? Equation 3 is this one. Dou mu I by dou T at constant pressure N is equal to minus Si. So what we get is dou mu I by dou T is minus Si. Is what it is, right? Dou mu I by dou T is minus Si bar. So we get equal to T into minus Si bar minus mu I divided by T square. Okay, and then substitute 4 in equation 6. Equation 4 is minus SI bar is equal to mu I minus mu I HI bar upon T. So we substitute for SI bar in this equation, and you'll get mu I minus HI bar just a minute. Okay, so T into SI bar, right? So we are substituting T into SI bar. T into SI bar is equal to mu I minus HI bar. So this whole term is mu I minus HI bar minus mu I. So mu I will go out. So what we get is delta mu I by T divided by delta T at constant pressure N is equal to minus HI bar by T square. And enthalpy is measurable. Partial molar enthalpy, we can measure it when we add one component to a solution. And that's why we have taken this form of equation, because we need to get this measurable quantities here. Temperature can be measured, enthalpy can be measured. Partial molar enthalpy can also be measured. Okay, so equation 7, is it okay? Is it clear?
Sir, why did we take the derivative?
The derivative of what?
Mu I by T.
Yeah, because if we take mu I, we will not get a what you call simple equation here. We need to have a simple equation here. That's why we have taken mu I by T, derivative with T. Ultimately, we want effect of temperature on mu I. But this mu I is a function of temperature. That's why we have taken mu I by T. And this time we get a simple equation on the right hand side. Any other questions? Any doubts on equation 7? Any other questions on equation 7? If we take above mu I by delta T, we will get some complex terms on the right hand side. That's why we are taking this thing. And mu I is a function of, you know that, it's a function of pressure, temperature, compositions. So we have instituted T here, so simplify the right hand side. Okay, so if you have now understood what is chemical potential and effect of temperature and pressure on chemical potential, now we need to see how to calculate or evaluate the chemical potential. Because if we are going to use it for our equilibria, we need to have some way of calculating or evaluating the chemical potential. Like temperature for thermal equilibria, you can directly measure. Pressure for mechanical equilibria, you can directly measure. But chemical potential directly is not measurable. Just like entropy is not measurable, chemical potential is not directly measurable. So we need to find ways of getting the value of chemical potential. And so we define another term called fugacity. Fugacity has a Latin origin, which means fleetness, or how quick it is, or escaping tendency, how fast it can escape. And it is used to represent behavior of real gases and used in study of phase and reaction equilibria involving gases at high pressure. We'll see why high pressure. Okay, so fugacity is essentially how fast something can escape, especially gases. Right, so if you take say a balloon and you pump in say air into it, and if it is pressure is increased, what happens? What happens to the balloon if you keep increasing the pressure or keep blowing air into the balloon?
It will burst.
It will burst, right? So gas has an escaping tendency, right? It cannot, maybe the balloon itself is weak, but it has some escaping tendency. And we are using fugacity to measure the escaping tendency or how fast it can escape for real gases. The key concept is real gases, not ideal gases. Ideal gases is very easy. We can measure pressure for ideal gases, PV by RT, and equation is there to predict all the properties. But for real gases, it is not easy. And what is the difference between ideal and real gases? What's the difference between real and ideal gases? Who can tell me? You done thermo one, right? Real gases, ideal gases.
Sir, can you repeat the question?
What is the difference between real gases and ideal gases?
Sir, in ideal gas, we assume the negligible molecular attraction between molecules.
What is it? Assume.
Negligible intermolecular forces.
Okay, yeah. What else?
Pressure we consider at zero, so that doesn't really happens in real gases.
Uh-huh. Yeah. What else?
We consider the volume of molecules negligible.
Yes. Consider volume of molecules negligible. Yes. So if you take say a box or rectangular box containing ideal gas or air in it at say low pressure or 1 atmosphere, that's also fine. 1 atmosphere is also quite low. So in that case, the molecules are not very close. Although we cannot see the molecules with our eyes, the molecules are not very close to each other. And if they are not close to each other, the forces of attraction are negligible. Why is it negligible? What is the equation for force of attraction between molecules? फिजिक्स में पढ़ा होगा ना, attraction between two particles, force of attraction between two particles. Okay, so if you take Earth and say Moon, how do you calculate the force of attraction between Earth and Moon? Is there any force of attraction between Earth and Moon? है कि नहीं है?
Yes, sir.
है. So how do you calculate?
Sir, capital G into M1 into M2 upon R square.
Exactly. So that's how you calculate the force of attraction between any two particles, any two objects, right? It could be solid, it could be liquid, it could be vapor, whatever. There are between molecules also there is some force of attraction, which will depend on mass of the molecule divided by r square. So distance between the molecules. So if the distance is more, the force of attraction will be less, r square, 1 upon r square, right? So if this distance between molecules is significant, the attraction between the molecules is not going to be that much. Right? And the other thing which mentioned was molecules themselves occupy a very small volume compared to the total volume of the gas. Because the pressure is very low, the molecules are very far apart. You cannot see, but yeah, you know that there is a lot of empty space in the container. Right? And if you increase the pressure, suppose I increase from say 1 atmosphere to 10 atmosphere, or 100 atmospheres, 50 atmospheres, So what happens? The distance between the molecules reduces because I have the same amount of gases in the container, but I'm increasing the pressure. So that will force the molecules to come closer to each other. When they come close to each other, the force of attraction will increase, right? M1, M2 upon R square. If R square is reduced, the force of attraction increases. Is that right? बराबर है कि नहीं? If the pressure is increased, the molecules will come closer. When they come closer, the force of attraction will increase between them, right? And that's when they start behaving like non-ideal gases. And that's what we call real gases. And in that case also what will happen, because the molecules are closer to each other, they occupy a significant amount of volume of the container. The empty spaces are reduced. ठीक है, समझ में आया difference between ideal gas and real gas? And if you remember Van der Waals equation, what is Van der Waals equation? You can tell me Van der Waals equation. Van der Waals equation याद है कि नहीं? किया नहीं thermo 1 में? You've done all this in thermo 1, right? So what is Van der Waals equation? Nobody remembers. Devendra?
Sir, P plus A by V square into V minus B is equal to RT.
Correct. Excellent. So what does it represent when you say P plus A by V square? What does it represent? A by V square? What does it represent?
The ideal gas pressure.
Intermolecular forces.
Molecular forces, increase in molecular forces, right? When you increase the pressure, the volume reduces, right? One more molecules occupy less volume. So plus A by V square. So lower the volume, the higher will be the pressure, right? P plus A by V square. So effective pressure will be P plus A by V square. That means if I keep increasing the pressure, what will happen is the volume will keep decreasing and the molecules will occupy more space. So that is the effect of or effective pressure. P plus A by V square is effective pressure of a gas which is not ideal or which is at high pressure. Is that okay? Is that understood? P plus A by V square, what does it mean? Ultimately it is same. P into V is equal to RT, right? Instead of P into V, we are saying P is replaced by P plus A by V square. So if it is effective pressure of a real gas, and V minus B is what? What is B? Small b?
वो molecules का जो volume है वो भी reduce
Yes.
करना पड़ेगा.
Right. So we are saying effective volume is V minus B. That means we are reducing the space or volume of molecules, right? So because we said initially molecules do not occupy too much space, right? But if you have high pressure or real gases, they occupy a significant space. So we have to take effective volume. It's V minus B. So effective pressure and effective volume is equal to RT, similar to ideal gas, right? So similarly, when we talk about fugacity, when you take high pressure, the molecules come closer to each other. There will be more force of attraction between them. They will occupy a significant volume. So we have to account for that. How does pressure change for a real gas, which is not behaving as ideal gas? That's why we introduce the concept of fugacity. Okay? So let us see how do we define fugacity. So we have this equation dG is equal to VdP minus SdT. And for isomer conditions, dt is equal to 0. So what you get is dG is equal to VdP. If we take ideal gas, and take 1 mole of ideal gas, we get V is equal to RT by P. So if you replace in this equation, we get dG is equal to RT by P into dP, which is nothing but RT dln P. dP by P is dln P. Okay? So what we get is dG is equal to RT dln P for ideal gas. Equation 1. Is it okay? Is it clear? Any questions, doubts on this one? We are talking about ideal gas now. So for ideal gas, we have derived what is the effect of pressure on Gibbs free energy. Okay, if there are no questions, we'll proceed. So if we represent the effect of pressure on Gibbs free energy of real gases by a similar relationship, this is for ideal gas, right? P is equal to RT dln P. Then the true pressure in this equation, that is P, should be replaced by an effective pressure, which is called fugacity. So now what we are saying is, if I can use this equation for ideal gas, I want to use similar equation for real gas, but I want to define some other term for P, because P is not applicable for real gas. We have seen that for van der Waals also, right? We take P plus A by V square. We don't take P. So we have to define a similar term which will be replaced for P, and that we can use for real gases, and that we call as fugacity. And that is what we call as effective pressure. Instead of P, we use F as fugacity, and we write dG is equal to RT dln F. So now instead of P, we have F, and this can be used for real as well ideal gas. For real gases, F is equal to P. For ideal gases, we have to find out F, fugacity value. So any doubts, questions on equation 1 and 2? Equation 1 is for ideal gases. We write a similar equation for real gases by replacing P with F, which is called fugacity, and that we call as effective pressure for real gas. समझ में आया? How we get this equation for real gases? Anybody has any doubts? Because this concept understanding is important. We are going to use this chemical potential and fugacity throughout our thermo, all units. This is the basis for everything else. Okay. प्रतीक्षा मोरे समझ में आया क्या?
हाँ सर समझ में आया।
पक्का? मैं तो पूछा अभी भी और भी. I mean just I am asking you because you asked the question, because और भी हो सकता है. रितेश कोल्हापुर समझ में आया क्या?
हाँ सर थोड़ा थोड़ा समझ आया।
थोड़ा थोड़ा क्या होता है?
सर वो फुगासिटी का कंसेप्ट थोड़ा सर फुगासिटी का कंसेप्ट थोड़ा नहीं समझा। एक्चुअल में क्या होता है वो?
Actually it is basically, see जैसे अभी आप van der Waals इक्वेशन में P plus A by V square क्या होता है, ये समझ में आया कभी? आज समझा क्या?
करेक्शन होता है ना?
करेक्शन होता है. समझा क्या? लेकिन क्यों करेक्शन होता है बता ना, मैंने अभी थोड़ी देर पहले. व्हाट इज दैट करेक्शन फॉर?
सर वो नहीं समझा।
हाँ वो भी नहीं समझा. रियल गैस और आइडियल गैस का डिफरेंस समझ में आया?
हाँ सर, यस सर,
समझ में आया ना?
हाँ.
सो रियल गैस में क्या होता है, डिफरेंस क्या है आइडियल गैस के और रियल गैस में?
वो इंटरमॉलिक्यूलर फोर्स कांस्टेंट होते हैं.
कांस्टेंट नहीं होते, बढ़ जाते हैं. कांस्टेंट कुछ नहीं होता है. Intermolecular forces increase because the molecules are closer to each other. The distance between the molecules is reduced. जितना नजदीक आएगा उतना attraction बढ़ता है, right? So if you are,
yes,
I'll give an example. If you are sitting in a class, you are sitting in one corner, and your one of the classmates is sitting in another corner. तो friendship हुआ क्या?
नहीं. Nice, sir.
Sitting in one corner of the class and one of your classmates is sitting in another corner of the room.
कांटेक्ट में
Friendship
आएगी
होगा
तो
होगा friendship?
नहीं सर,
नहीं
कांटेक्ट में
होगा.
आएगी तो
And if you are sitting close to each other on same bench, क्या होगा?
yes,
Interaction.
Interaction बढ़ेगा, right? Interaction बढ़ेगा, force of attraction बढ़ेगा, you start liking each other, you understand each other. So that is what this is in a way, right? If you come closer to each other, then you understand each other. You understand what he likes, what he doesn't like, क्या है, क्या नहीं है. So that's what it is. You are talking about force of attraction and repulsion. It could be repulsion also. You sit with somebody today, you don't like that person. Tomorrow you say, I'll not sit with that person. होता है कि नहीं?
Yes, sir.
होता है. See, because you don't initially you don't know whether you are going to like a person or not. नए नए आते हैं कॉलेज में, you sit with somebody, and then that person will say something, you say something, you don't like each other. Next day you are sitting somewhere else. So this is what we are talking about. We are talking about forces of attraction or repulsion between molecules or particles, and they increase. That's why the pressure increases. Right? I mean, pressure is representing कि क्या escaping tendency है गैस का. जितना ज़्यादा pressure होगा उतना fast भागेगा गैस. Right? Because we saw P is a driving force for mechanical equilibrium, right? Pressure. है कि नहीं? Like temperature for thermal equilibrium, pressure is for mechanical equilibrium. जितना हाई प्रेशर रहेगा उतना फास्ट भागेगा, उतना ज़्यादा फास्ट वो ट्रांसपोर्ट होगा. बराबर. So now what we are doing is we are saying that we cannot use pressure for real gases because that's not representing the property of real gas. Pressure is okay when molecules are far apart. We can use that as a way to quantify ideal gases, because we understand ideal gases and pressure represents ideal gases very easily. But when the molecules come together, we cannot represent it by pressure. That driving force cannot be represented by pressure. So we have to replace it with some other term which is similar to P, but not exactly P. So we define another term called fugacity, which is for real gases. It can be used for ideal gases also, but essentially we define it for real gases. तो ये इक्वेशन था dg, change in chemical potential, Gibbs energy, changing Gibbs energy was a function of pressure for ideal gases. Now we are saying now it is a function of fugacity for real gases. It's similar to that. It's called effective pressure for real gases because pressure of real gases cannot be measured. I mean, the interaction between them cannot be measured. So we define a term called F. It's a theoretical concept, but similar to P.
सर पर इसका कहाँ पे यूज होता है फ्यूगेसिटी का? ये कैसे यूज होता है?
We'll see how to use it. We define किया है, now we'll use it because see क्या ना, we cannot measure G. मैं बोला ना, this energy we cannot measure, chemical potential we cannot measure, right? जो हमने define किया था chemical potential कहाँ गया ऊपर में, जो हमने देखा chemical, we cannot measure it because temperature can be measured, pressure can be measured, but pressure can be measured, but chemical potential cannot be measured, right? So we have to define a term which can help us to actually measure chemical potential. So that's why we are defining this thing. And then we'll see how to actually quantify or calculate F, fugacity. Measure वो भी नहीं होगा, लेकिन calculate कर सकते हैं fugacity हम. And once we calculate fugacity, we can calculate Gibbs energy. Gibbs energy मिल गया तो chemical potential मिल जाएगा. That's how we are defining all these terms to actually measure chemical potential, which is what is important for us. समझा क्यों डिफाइन कर रहे हैं सब? The ultimate objective is to find the value of chemical potential, which is a driving force for phase equilibrium and chemical equilibrium.
हाँ सर, वो समझा.
समझा? और किसी को डाउट है कुछ, why we are defining all these things? Because it's a very vague term. I understand it's not easy to understand fugacity. Chemical potential फिर भी समझ सकते हैं, partial molar Gibbs energy, but fugacity understanding is not easy. But once you understand it, that it is just, if you look at ideal gas, we replace pressure with fugacity, and we are defining fugacity as effective pressure for a real gas. इतना समझो. That is important. And then we'll use it to calculate fugacity for ideal real gases. And once we get fugacity, we can calculate Gibbs energy. Once we calculate Gibbs energy, we can calculate chemical potential. So indirectly, we are calculating chemical potential for real gases. Any doubts, questions so far? No? Okay, so once we have this equation 2, we can integrate it, and we get G is equal to RT ln F plus some constant C. Okay, so I'll quickly cover this concept. I'll repeat it tomorrow. ऐसा कुछ नहीं है, इसको repeat करेंगे. So now we need to define a standard state of fugacity. What is standard state? जैसे अभी temperature, right? Temperature scale पता है आप लोगों को? What is temperature scale? टेम्परेचर स्केल नहीं पता लोगों को? दीक्षिता, व्हाट इज टेम्परेचर स्केल? ये भी थर्मोवन में पढ़ा हुआ आपका. व्हाट इज टेम्परेचर स्केल?
सर इट इज केल्विन.
अरे केल्विन है, बट स्केल क्या है? केल्विन है, रैंकिन है, फ़ारेनहाइट है, सो मेनी है, राइट? बट हाउ वाज इट डिफाइंड? इसने डिफाइन किया कि आइस 0 डिग्रीज पे मेल्ट होता है, वाई नॉट 5 डिग्रीज पे? किसने डिफाइन किया कि आइस वाटर 100 डिग्री सेंटीग्रेड पे इवेपोरेट होता है, वाई नॉट एट 90 डिग्रीज? हाउ वाज इट डिफाइंड?
सर ऐसा है कि जब मतलब वॉल्यूम 0 हो जाता है किसी गैस मॉलिक्यूल का, तब टेम्परेचर 0 केल्विन होता है.
नहीं, वो ठीक है. आई एम नॉट टॉकिंग अबाउट केल्विन. आई एम आस्किंग कि अभी आइस का मेल्टिंग पॉइंट है या वाटर का फ्रीजिंग पॉइंट 0 डिग्री सेंटीग्रेड रहता है, राइट?
हाँ.
So why is it 0 degrees? Why not 5 degrees? Boiling point of water is 100 degrees. Why not 100 degrees, 110 degrees or 90 degrees centigrade? Why was it defined as 100? समझ रहे मेरा क्वेश्चन? So it was arbitrarily defined. We define किसी के जहाँ आइस मेल्ट होता है at 1 atmospheric pressure, we know that temperature and we say that is 0 degrees centigrade. That's how the scale was defined. And then somebody said कि ठीक है, I think it was Kelvin और जो भी रहेगा, जूल रहेगा, जो भी रहेगा. He said कि water boils at a certain temperature at 1 atmosphere. The pressure is constant. Water will boil at the same temperature, and we define that as 100 degrees centigrade. That is also arbitrary. You could have said 90 degrees, doesn't matter. तो उसके बीच का डिवीजन स्केल को डिवाइड कर दिया इक्वली between 0 to 100. So you have defined a standard state. This is a standard state. I says 0 degree centigrade standard state for temperature. Water boiling at 1 atmosphere pressure, 100 degrees centigrade is defined as standard state for temperature. Similarly, we have to define a standard state for fugacity also, because we need to measure. Right? So we are going to define a standard state of fugacity similar to temperature scale. So let us see two states, say state 1 to state 2. Gibbs energy is G1 in state 1, G2 is in state 2, and fugacity is F1 in state 1, F2 in state 2. So you can write this equation for both the states. G1 is equal to RT ln F1 plus C, G2 equal to RT ln F2 plus C. So if you take a difference, you take G2 minus G1, which is change in free energy, is equal to RT ln F2 by F1. C will cancel out. You get F2 by F1. Right? So free energy change can be experimentally measured by using equation 3. We can calculate F2 by F1. So if you can measure delta G, then we can calculate F2 by F1. We are doing all this just to measure. कैसे नहीं define तो कर दिया terms. जैसे arbitrarily हमने scale define कर दिया 0 degree centigrade for ice. Now we have to define some state for fugacity also similarly, right? So fugacity in any state. Now you know from delta G we can calculate F2 F1. But again F2 F1 क्या है? We don't know. Right? So fugacity in any state can be evaluated if the fugacity is assigned a specific value in a particular reference or standard state. So if you define F1, what is F1? What is standard state? If you define F1 as standard state, then we can calculate F2 because we know what is delta G. समझा क्या? Why we are defining standard state? I think we'll continue tomorrow. It will take time for this thing. Think about it. I'll repeat the standard state. We'll continue tomorrow. But fugacity, थोड़ा सोचो उसके बारे में. Try to understand what is fugacity. And I think there are many videos available on YouTube. You can see some of them. It will help you understand. Okay. I'll also show you something tomorrow. Okay. Any doubts, questions? Fugacity we'll cover tomorrow again.
सर NPTEL के नहीं हुए क्या?
हाँ?
NPTEL चालू नहीं हुआ क्या?
NPTEL will start on 14th of September. Postpone हो गया. Because of this COVID, I think they postponed it to 14th of September. मेल आया होगा ना आपको?
हाँ सर मिला है.
मेल आया था लास्ट वीक ही मेल आया था कि 14 सितंबर स्टार्टिंग डेट किया अभी. Because of COVID सब जगह प्रॉब्लम से इसीलिए they have stopped or postponed it. ठीक है, so I'm stopping the recording now.